So this is my lab report for Physics 2212 Lab 2, where we're revisiting the charge tapes lab in Lab 1. To introduce this lab, the purpose of this lab is to reuse some of the principles and ideas from Lab 1 by splitting the total charge on the tape into individual charges that we're going to call DQs. And what this does is it separates the idea of the tape as a single point charge. The tape has multiple point charges. This is a preview of the GlowScript output graph that I made. And these are the fundamental principles I used. So the magnitude of force of gravity, magnitude of force of electricity. These are essential for this lab, just like the last one. And then also force equal to mass times acceleration, which in this case is 0 because we want the force of gravity and the force of electricity to be balanced. So just to reiterate what we did in Lab 1, so we had two tapes, tape A and tape B, and we put them on top of a surface tape, and then we ripped it off of the surface tape in order to put a positive charge on both tapes. And then we kind of bridge tape B like this, and when we move tape A towards it, it repels because they both contain a positive charge. So I still used the same mass of the tape as I did last time and the same distance as I did from Lab 1. However, the charge is a little different because it's not treated as a singular point charge anymore, which is what I'll talk about on the next slide. So we still have the same assumptions, especially that air resistance is negligible as a force. But obviously now, instead of one big point charge, we have individual point charges in a line right here for our GlowScript model. So this is the start of my model, the part 1. We have our constants right here that are mainly the same, right? Our mass for the tape A stayed the same. However, I did have to change Q, right? So this is the Q I calculated in coulombs in Lab 1. That worked well to cancel out the force of gravity. However, it did not work well, and I'll talk about that later with the GlowScript output. And through calculations, this became the proper Q we want to use when we're dividing into little DQs in order to make the force of electricity, the electric force overall, equal to the gravitational force. Then this is my E field function, which just takes into account the charge constant 1 over 4 pi epsilon 0. And then we have R, so we split it into magnitude and R hat, and this just returns the equation we had in the introduction slide. So some more of my coding here. So we have we made two objects. So top tape and bottom tape are objects which have the same mass, have the same charge, overall charge, and then you can split it into however many DQs here that you want. Then we iterate through the top tape entries, right? And also iterate through the bottom tape entries in order to get every single DE possible. So DE as in each tiny electric field exerted by each DQ on other DQs in tape B. And so we keep adding that so that we get a total E right here. This is the GlowScript output I have. So on the left, you see that these numbers don't match up. And obviously these green arrows aren't as big as these green arrows, and that's largely because when you use the Q from the previous Lab 1, it's not big enough. So through algebraic manipulation, I changed my Q to what it is now that I showed in the constant slide, and I made sure that electric force and gravitational force were equal with that Q. Some possible sources of error, same as last time, there might have been other forces we didn't account for. And in Lab 1, I might have measured dimensions incorrectly or touched the sticky side of the tape. Also, because this is a mostly a computational lab for Lab 2, there's possible coding error that could exist in this lab. So finally, to wrap up with discussion questions, first one, what if we had modeled each tape as a single point charge, as in we did with Lab 1? And I have shown the charges I got from Lab 1 versus Lab 2. And you can obviously, there's about 1.58 times increase for the one in Lab 2 because it's more essential to have those DQs. It's more realistic, which leads us into the second question. Why do these estimates differ, which I already answered, but which value is more likely to be closer to the real value? I believe that the one from Lab 2 is more accurate because when you separate the charges, it makes the value of the big Q more accurate. Because in real life, we're not going to model a single piece of tape as one point charge, right? It's not something we can accurately represent, but we can want to represent on a smaller level a lot of separate point charges instead of just one.